Hello everyone. So the last method in this module is the unit load method. So in this unit load method, what we do is we apply a unit load. It's there in the name itself. So that is nothing but the unit load. Unit means one. 1 kilonewton load will be replaced. We'll be replacing this external load, whatever is the external load P. So we'll be replacing that with a unit load, and we'll find out the deflection. So to find out the deflection, the formula is slightly different. That is delta is equal to 0 to L capital Mx into small mx divided by EI into dx. Now, where capital Mx is the moment due to moment at the section X due to the applied load. So it is moment, bending moment at the section X due to the applied load, that is the external load. Whereas small mx is nothing but the bending moment at the section XX due to the unit load, that is 1 kilonewton load. Okay, so let us start with the problem. I can see here, find the unit, find the reflection using the unit load, and it is nothing but again complete span, AB span of length 7 meter. Again, 50 kilonewton is the eccentric load which is placed here, and EI value is given. So again, it is given in kilonewton and meter square and meter. So you can directly multiply E into I. There's no simplification, so directly you can multiply and you'll get the value of EI. That is 2800 kilonewton meter square. So again, they've asked you to solve this by unit load method. So in unit load method, what we do here is we'll find first the reactions. You can see here, this is 50 kilonewton. For this given external load, find out the reactions as usual. So again, to find out reactions, same thing. Summation H is equal to 0, summation V is equal to 0, and moment about A is equal to 0. So we'll find moment about A is equal to 0, and RB into 7 complete length, then 50 into 3. So we'll get RB, then 50 minus 21.42 is RA. So we'll get the reactions both RA and RB. Okay, once you find the reactions, now what we'll do here is we'll apply the unit load method. So unit load method is wherever this load is acting, that external load will be replaced by 1 kilonewton. So you can see here, again, it is a ABC. Complete length is AB, and exactly at C, that is a distance 3 meter. I've removed this 50 kilonewton load and I've applied only 1 kilonewton load. So this is called as unit load. So again, as usual, for this unit load, I'll calculate the reactions here. So moment about A is equal to 0, RB into 7, then 1 into 3. So you'll get RB and RA. So calculate RA and RB, write it here. So now see here, this is reactions due to the external load. This is the reaction induced due to the point load, or it's called as unit load, 1 kilonewton. Okay, so once you find these reactions, now what we'll do is we'll cut the section here and here. So according to the formula, what the formula says is moment due to external load in that span, moment due to the unit load in that span. Okay, so we found out the reactions. Next is we'll calculate the moment. Now to calculate the moment, it's always easy to draw and use the tables. Okay, because it is not symmetric beam, so we will use the table. So first portion AC, BC. Next origin. Origin of AB is A, AC is A, BC is B. Then the limits 0 to 3, 0 to 4. Okay, now see here, bending moment. Capital M is bending moment due to the external load. So we'll go to the first diagram. So in AC span, left side only there is one moment. It is RA is going clockwise. So it is 28.58 into X. Written here 28.58 into X. Similarly to the right side now. When again in this portion, I'll cut the section here. So to the right side, anticlockwise load, anticlockwise moment is positive. So it is 21.42 into perpendicular distance. I'll cut the section here. So I've written it here, 21.42 into X. Next, similarly, MX, small mx is nothing but I'll go to the second diagram. Again, I'll cut the section here to the left side, 0.57 into this distance. Next, when I cut the section here, 0.43 into this distance. Okay, so EI is same throughout. Okay, so once you get these values, next thing is only substitution and simplification. Okay, so first write the formula delta is equal to 0 to L mx into capital Mx into small mx divided by ei into dx. So it is 0 to 3. So 0 to 3, capital M into small m, same capital M into small m from this table, multiply. So find common, so it is x square, again multiply this, again x square. So x square becomes x cube, there also becomes x cube. Then substitute the value 3 cube, 4 cube. So then delta is 343 divided by ei. Now that you know the value of ei, so divide it by ei value, that is 2800. So it is now 2800. So that is nothing but 0.122 meter, because all these are in meter. Okay. All right. Similarly, now calculate. Next thing is, I think we'll first finish off with the, so this is a frame. So first we'll finish off with the beam type of problem. Okay, so the next beam type of problem is determine the deflection and rotation at the free end of a cantilever by unit load method. So in this problem, they've asked you to find both deflection and rotation at the free end. So you have to find delta C and theta C at this point. Okay, so they've also given you the value of E and I. This time E and I, the units are different, so it is Newton per meter. You have to convert both of these into kilonewton and meter. So as usual, so first write this E, first let us say see the conventions. So 2 into 10 to the power 5. So Newton to kilonewton 10 to the power minus 3. Then divided by, so it becomes kilonewton divided by meter mm square. Mm to meter, so 10 to the power minus 3 square into I. 12 into 10 to the power 6 into, so it is mm to meter is 10 to the power minus 3 raised to 4. So multiply this, solve this, simplify, you'll get this EIS 2400 kilonewton meter square. Okay, so again in this given beam, what they've told is you have to find deflection and rotation at point C. So this is the original beam. So what I'll do here is, wherever they've asked you, they've given load at point B also and at point C also, but they've asked you to find out deflection rotation at C. So by using this unit load method, what we'll do is we'll remove this load here, all the loads, and only at that point C we'll apply a unit load, 1 kilonewton. Okay, so first in the original beam, what we'll find is we'll find the deflection at point C. So let x be the distance from BC. Okay, so again as usual, because there are two loads and two different and important thing is there are two different values of I. One is I here in BC, and AB it is 2I. Okay, so as usual, first we'll find out. So this is the original beam, we're cutting this original beam, and next is in this unit load beam, so only at point C I'll apply unit load 1 kilonewton. Okay, so first thing is portion AB BC. Okay, then origin for AB is B, origin for BC is C, then limits 0 to 2, 0 to 2. Next, bending moment, capital M. So bending moment at a section XX. So bending moment at a section XX is now in AB span. That means in this span, AB span, it is first 20. Okay, 20. You have to reach to this span. So it is X plus 2. Okay, so 20 into X plus 2. Next, this is plus 20 into X. Okay, just 20 into X. Next, in BC span, so in BC span to the right side only one load is there. That is 20 into X. We have written it 20 into X. Next, bending moment MX. Okay, so MX is equal to now, okay, we'll come to this section. So in this section in AB span, so it is 1 into X plus 2. X is this portion plus 2. Again, why I'm cutting this X here is in AB span, we'll cut only that span. Okay, only cut the section that span. Okay, so it is now 1 into x plus 2. So you can write it as 2 plus x or x plus 2. Next, similarly, when I cut this section here, so right side only one load, that is 1 into x. So 1 into x. Once you get this capital Mx and small mx, and next is be careful about EI values also. So in AB it is 2 EI, in BC it is only EI. So now apply the unit load. So once you apply the unit load, so it is now delta C is equal to integration 0 to L capital Mx into small mx divided by EI. So capital Mx, small mx. So use these values, capital Mx into small mx, capital Mx into small mx. So multiply these, capital M into small m. Okay. So if you go on solving this, so you can see here, this is like x square plus x plus constant c, and multiply this properly. So what you do here is 1 over 2 ei, take it common. So x square, it becomes cube, x becomes square, 80 becomes x. Okay, 1 over 2 ei, so this becomes 20 x cube by 3. So once you start solving this, so substitute the value of 2, 2, 2, and here also 2. Once you solve this, so you'll get 306.68 over EI. So now that you know the value of EI, substitute the value of EI here. So that becomes delta C is equal to 0.127 meter. Again, the answer is positive. That means it is acting downward. Okay, so the next part of the question is they have asked you to find the rotation. You find the deflection at C, to also find the rotation at C. So now to find the rotation at C there is no moment. So you have to apply a dummy moment. So whenever there is no whenever there is no point load given at that point where you have to find the deflection, you have to artificially induce a dummy load. So again here, to find rotation at the C, there is no moment acting. So we'll apply a dummy moment, that is 1 kilonewton meter moment. So apply moment at C. So we'll apply like this, clockwise moment. Okay, again, as usual, portion AB, BC. So these are only loads, AB and BC. So origin of AB is B, origin of BC is C. Then limits is again 0 to 2, 0 to 2. And now finding the bending moment. Okay, now see here, moment due to the capital MX is bending moment due to the external load. Now when you check out this diagram, bending moment due to external load, so this is 20. Okay, it is 20 into x plus 2 in AB span. So in AB span it is 20 into x plus 2 plus 20x. What we have done before, same thing. This would be same. Original bending moment would be same, that is 20, what we have done it here, 20 into x plus 2, 20 into x plus 2. Next, when you cut this part of the section, it is 20 into x. Okay, that would be same like before. So when you add this and multiply, it would be same. Next, in BC, it would be the total load, that is 20 into x. So bending moment in AB and BC would be same. So there is one complete moment acting throughout the beam. In AB also it will have the same impact. BC also it will have the same impact. So EI is 2 EI and here it is only EI. Now apply the unit load method. When you apply unit load method, again it is theta C is equal to 0 to L. Theta C is equal to 0 to L mx into capital MX into small mx divided by EI into dx. So now 0 to L, so 1 over 2 EI, take it common. So capital, this is M into small m, again same, M into small m. So multiply these. So once you multiply, then integrate. After integrate, substitute the values, then you'll get 120 over EI. Now that you also know the value of EI, substitute the value of EI, then theta C is now 0.05 radian. So theta is always measured in radian. Okay, all right, that's it for today. Thank you.